So next up, let's talk about some parameterizations of conic sections. Now there are 4 different kinds of conic sections. We're going to start with what I would consider to be the most basic one, the circle. Now when we started trigonometry, it started with the unit circle. The unit circle was x squared plus y squared is equal to 1, and we defined x to be equal to the cosine of theta and y to be equal to the sine of theta. And you know what? That worked out pretty darn well. So much so that there's not really a whole lot of improvement to make on it, except that not every circle is the unit circle. So anytime we needed to beef it up and say that x squared plus y squared is equal to r squared for a circle of radius r, we could say that x is equal to r times the cosine of theta, and y is equal to r times the sine of theta, with, once again, theta going from 0 to 2 pi. However, if we want to get to the most general sort of circle, the standard form of a circle is x minus h quantity squared plus y minus k quantity squared is equal to r squared. This is a circle whose center is located at hk with a radius that's equal to r. Now everything that we do here is based off of the Pythagorean identity, where we say that x is the cosine, y is the sine, therefore x squared plus y squared is equal to 1. So the idea is we're going to take this thing that's inside here, and we're going to say that this is going to be equal to r times the cosine of theta, and that this thing in here is going to be equal to r times the sine of theta. Except we're not going to use the parameter theta, we're going to start using the parameter t. Now, to finish solving this for x, we would need to add h, and to finish solving this for y, we would need to add k. As a result, this is what I would consider to be a fairly common parameterization for a circle that's centered at hk with a radius of r. X is equal to h plus r times the cosine of t, and y is equal to k plus r times the sine of t. Now this lends itself really nicely to the idea of an ellipse. An ellipse is something that is also round, but is not exactly circular. Standard form of the ellipse would be x minus h quantity squared divided by a squared plus y minus k quantity squared divided by b squared is equal to 1. This is indicative of an ellipse with a horizontal major axis. From the center at hk, this would extend a units left and right, and b units up and down. So the idea is we're going to go straight back to the Pythagorean identity one more time. We're going to say that this whole thing is going to take on the role of the cosine squared of t, and this whole thing is going to take on the role of the sine squared of t. That way the cosine squared of t plus the sine squared of t is equal to 1. With that in mind, if we actually set this equal and then solve for x, we'd have to multiply by a squared, take a square root, and then add h. This would be h plus a times the cosine of t. And then do the same thing for y. Y would be equal to k plus b times the sine of t. Then once again, allowing t to go from 0 to 2 pi would be one full rotation in the positive direction around this ellipse, starting at the rightmost point and ending at the rightmost point, just like the definition for right triangle or unit circle trigonometry. Now this also takes us nicely to the hyperbola. The hyperbola is, for all intents and purposes, the exact same thing as the ellipse, except instead of with a plus sign in between them, there will be a minus sign. So with that in mind, a hyperbola has standard form x minus h quantity squared over a squared minus y minus k squared over b squared is equal to 1. Now with that in mind, I would like to ask you to recall with me another one of our Pythagorean identities where we can have a difference of two squares being equal to 1. This would work with both the secant and the tangent, as well as with the cosecant and the cotangent. We tend to go with the non-co functions just because. So we're going to do the exact same thing as what we just did for the ellipse, except instead of using cosine squared and sine squared, this time we're going to be using the secant squared and the tangent squared. That will allow us to retain the minus sign that's in between them. Now, the algebra is literally identical to what we just saw. This would be h plus a times the secant of t, and y would be equal to k plus b times the tangent of t, allowing t to go from 0 to 2 pi, and omitting the two places where it's undefined, which would be pi over 2 and 3 pi over 2, all will be well. Now, my classes don't typically study this, but there is another way to make this work, and that is through the use of what is called hyperbolic functions. Now, the reason that they're called hyperbolic functions is that they are based on, well, hyperbolas. The corresponding Pythagorean identity that we would have is that the hyperbolic cosine squared of t minus the hyperbolic sine squared of t is also equal to 1. That's what's intended by the cosh and the sinh of t. So within some mathematical circles, they would define this all to be the hyperbolic cosine squared of t, and define all of this to be the hyperbolic sine squared of t. Just please be aware that if you see hyperbolic functions, chances are pretty good you're talking about a hyperbola. So doing literally all of the same algebra here, this would be x is equal to h plus a times the cosh of t, hyperbolic cosine, and y is equal to k plus b times the hyperbolic sine, or the sinh of t. Now for this one, based on their definition, t would just be any real number, and that'll get you the entirety of the hyperbola. Now again, if you don't study the hyperbolic functions, that's okay. You can just sort of disregard this one.